Hi, my name is Amr Schalberg, and this is the first video in a series on the basics of assembly language. The first set of skills that we will need to be proficient in is binary, hexadecimal, how logical operators and bitwise operations work, how data is organized into things like nibbles and bytes, and we will also take a cursory look at encodings. So what is data representation? Data representation is the way that data is stored or transmitted. Not all things see data the same way, so we need to be comfortable switching between different methods of representing data. Let's start by taking a look at the decimal system, and then we'll take a look at binary and see how we represent the same data with the decimal system, also called base 10, and the binary system, also called base 2 or 2's complement. Let's start with a review of the decimal system, also called base 10. So how does base 10 work? Well, it's a numbering system that we use every day, right? So this is just an example, 904. Well, in this first integer right here, we have the ones column, the tens column in the second, and the hundreds column in the third. So what does that mean to us? Well, that means in this first column, we have a number. Now, we've broken it down here so that it's a little easier, especially when we convert to other base systems. But what do we really do here? We bring 4, the first integer, to the 0th power, times 10 to the 0th power. So 4 times 10 to the 0th power is 4, because anything to the 0th power is 1. So we have 4 times 1 is 4. So we will add that to the next column. The next column has a 0, so we know this will be 0, but 0 times 10 to the first power. So 10 to the first power is just 10. So whatever integer we have in that second column would be itself times 10. And we'll add that to the next column over. And we have 9 in that position. So 9 times 10 to the second power. So 9 times 10 squared. Well, 10 squared is 100. So we have 9 times 100. So we get 900. So this represents the hundreds column in this integer. This is called a positional numbering system, where each column to the left is worth 1 base power higher than the one preceding it. Let's take a look at a second example in the decimal system. So here we have the number 116.21. So we'll start from right to left, and we have 1 times 10 to the negative 2 power. This will give us our 0.01. We'll move one column to the left where we have our 2, and we'll multiply that by 10 to the negative 1 power. Remember, this column is 10 times as valuable as this column. So we'll add that to our total sum. Right now we're at 0.21, and we'll add 6 times 10 to the 0 power. This will just give us 6 itself, plus 1 times 10 to the first power, which is just 10. So we're now at 16.21. And now we add our hundreds column. 1 times 10 squared, which is 100, which gives us the value of 116.21. Now, if that looked a little wonky to you, that's okay, because you really won't ever use the numbering system like that. What we're all more familiar with is looking at a number, we'll take 904 again, like this, and understanding that this represents the ones column, this represents the tens column, and this represents the hundreds column. Now, we know that intuitively because we use this number system every day, but this will hold true across this way of ordering them will hold true across all the numbering systems, including binary and hexadecimal. Something important to note in positional notation systems is that zeros to the left with no integer with a value ahead of them do not change the number. So for example, if we have 104, this can also be written as 104. This is also 104. And this is also 104. And this is true in binary as well. So if we have 1, 0, 1, let's say we have 5 in binary, right? Well, 5 in binary could be written like this. It could be written like this. It could be written like this. As long as there doesn't come a number ahead of here with a non-zero value like this, then this is always 5. So let's take a look at how binary works now. Now, binary really only has two major rule differences from the decimal system. The only digits we are allowed to use are 1s and 0s, and we have a base 2. So let's spread out the system like we did with the decimal system here and take a look at this notation, right? So we have our first integer, and we would multiply that by 2 to the 0 power. So we would multiply it by 1, so it is itself. So in this position, we have our 1s column. Now, keep in mind, this can only be 1 or 0, not only because we can only use the 1 or 0 integers, but because it's multiplied by 1. So this column can only represent 1 or 0. So we would then add that to our next column, which is our integer times 2. So this can represent either 0 or 2. We would add that to the next column, and we have our 4s column, because it's 2 squared, 4. So we would have our integer times 4, and it's our 4s column. Because it can either be a 1 or a 0, this can either represent 4 or 0. It will either represent 4 or represent nothing. Then we move to our third column. We have our 8s column, right? So we have our integer times 2 to the third power. This will either represent 8 or it will represent 0. This makes binary actually a little bit simpler than the decimal system. So if we go ahead and take a look at this number right here, you will see we have 10101. Well, let's take a look at what this represents. In our first column, we have 1. This is our 1s column. It represents the number 1. The second column is our 2s column, and it has a 0, so it represents 0. So this current number is 1. Now we move to our third column, which is our 4s column. This is our number 1 times 2 squared, so that is 4. So this is 4. So 4 plus 0 plus 1 is 5. 101 in binary represents 5. Now we'll move on to our 8s column, and our 8s column has a 0 in it. So that means that it represents the number 0, and we won't increase our number at all. And finally here we have our 16s column, and we have a 1. So 1 times 2 to the third power, which is 16, is 16. So the number we have here is 16 plus 0 plus 4 plus 0 plus 1. Or 21. And we can also, if that makes it easier, write out what these columns represent. So we have our 1s column here, our 2s column here, our 4s column here, our 8s column, and our 16s column. So another way to look at this is we have 1, 1, 1, 4, and 1, 16, 21. So now let's compare binary and decimal side by side and take a look at why this base notation is helpful when learning binary. So here up top we have a decimal number of 14, right? We have 1 in the tens column and we have 4 in the ones column. So we know intuitively that this number represents 14 when we're using decimal notation. Here we have an equivalent number. 0111 in binary represents 14. So let's take a look. Here we have our ones column, and here we have our tens column. Compared to the binary, we have in the 1 column we have a 0, so 0. In the 2's column we have a 2, so we have 2. In the 4's column we have a 4, so 6 is our total at the moment. And then in our 8's column, we have a 1, so we have 8. So we have 0 ones, 1 2, 1 4, and 1 8, or 14. Now you can see with the base notation how this kind of makes it in a similar language. So we have 0 times 2 to the 0 power, and we have 4 times 10 to the 0 power. Right? So you can see how the different bases are used here. 1 times 2 to the first power, 1 times 10 to the first power. Now, of course, because decimal notation is a lot more dense than binary, the number of positions you need are much smaller. Now this is probably a good time to start talking about notation because some of you will have noticed that we're going to run into a problem here. If it wasn't for the base notation down here on the bottom, you wouldn't be able to tell whether this was binary or not. 1110 is a perfectly valid decimal number. 14 is obviously not a valid binary number, but it is a valid hexadecimal number. So how do we know what we're looking at? Well, there's a couple of ways, and they're completely context dependent. One way that's common in mathematics is to use the base subscript notation. So you will have, for example, because this is base 10, you would have a 10 here. And because this is base 2, you would have a 2 here. Another way that's common, especially with assembly, is you may see, because you'll be dealing with binary, decimal, and hexadecimal numbers, is you may see a number like, let's go 15. So you could see this as 15H for hexadecimal. If you were dealing with a binary number, you might see this as binary. You might see a big B. Also representing binary. You may also see a 0B in front of the number. It is very context dependent, and so it is very important when you're working in anything and you have a chance of running across different numbering systems, octal, decimal, hexadecimal, binary, that you look for context or a key of some kind or any of the documentation that will help you know how you know which numbering system you're using at that time. So now that we know how binary works, let's have some practice and get really good at converting from binary to decimal. So let's take this first number, 101101. Now, I would encourage you to pause the video and go ahead and work this through by yourself. And assuming you've done that, let's take a look at what we've got. So we've got our 1's place here, our 2's place here, our 4's place here, 8, 16, and 32. So what do we have? We have 132 plus 0 16s plus 1 8, so we're at 40, plus 1 4, so we're at 44, plus 0 2s, so we're still at 44, plus 1 1, so we're at 45. Now you could do this the other way as well. You could go, okay, well I've got a 1, a 4, so 5, I have an 8, so 13, and 32, so I've got 45. So now let's work on the second one, 11010. Now again, pause the video and work that through yourself. And now that you've worked that through yourself, let's go ahead and check it. So we've got a 1 here, our 2's, our 4's, our 8's, and our 16's. Ooh, 16's. So we have 1, 3, nothing in the 4 column, 1 in the 8, so 11, and nothing in the 16 column. So remember, because this is a leading 0, this could be entirely omitted and it wouldn't change the value of this at all. So the number for this is 11, and we'll go ahead and write on the top one. This was 45. And now we have, for our third problem, go ahead and pause it if you haven't done this one already. And now that you've done it, 1, 1, 1, 1, 1, 1. So we'll have a value in each one of these columns. We have our 1's column, our 2's column, our 4's column, our 8's column, our 16's column, and our 32's column. So I think it's probably best to go from left to right here. So we have 32 plus 16. So we have 48 right here. In our 8's column, we have an 8, so we have 56. In our 4's column, we have a 1, so we have 60. In our 2's column, we have a 1, so we have 62. In our 1's column, we have 1, so we have 63. So 1, 1, 1, 1, 1, 1 in binary equals 63 in decimal. All right, I hope you guys found this helpful. We went over a review of the decimal system, how binary numbering systems work, and how to convert from binary to decimal. In the next video, we'll be going the other way and going from decimal to binary.